I'm sure that the expression dark matter is familiar to each of you. However, very few people actually understand what exactly is hidden beneath this seemingly simple name. And I'm not just talking about us mere mortals. Scientists also have very little idea what dark matter is. In the US and Europe today, billions of dollars are being spent on vast machines and complex equipment that aim to help us discover the nature of this mysterious stuff. So if we don't know what dark matter is, then how do we know where to find it? This is really strange and kinda cool. First, before we even begin to speak about it, it'll be necessary to at least understand where we learned about this mysterious matter in the first place. I'll give you a very simple explanation. Here we have a satellite. It's in orbit around the Earth. If we significantly increase its speed, then the Earth's gravity will no longer be able to keep it in orbit, and this big hunk of technology will fly out into open space. If we are interested in numbers, the maximum speed of this orbit around the Earth is 11 kilometers per second. If our planet were 100 times heavier, then the maximum speed would be 10 times faster. That is, the heavier an object is, the faster other bodies can rotate around it. This is how astronomers measure the masses of distant galaxies and clusters of galaxies. Austrian-American astronomer Fritz Zwicky was investigating such phenomena back in the 1930s. Investigating the velocities of single galaxies in clusters, he found that, on average, they move about 100 times faster than expected. It seems there was some sort of additional hidden mass there, besides the luminous mass that we could see. It made the galaxies move much faster than they should have. It was then that Zwicky first introduced the term dark matter to refer to this bizarre and perplexing mass. The science of space was really just beginning to emerge in the 1930s. Unfortunately, this meant that very few people paid due attention to this unexplained phenomenon. In their view, there was little of consequence that could possibly be there. Later, in 1970, two astronomers, Vera Rubin and Kent Ford, examined in more detail the rotational speeds of stars in the Andromeda Galaxy. Their results changed our view of modern astrophysics forever. The stars in the Andromeda Galaxy were rotating much too fast to be explained. This meant that there was still some mass, besides the stars, that we, for some mysterious reason, could not see in the Andromeda Galaxy. And judging by the rotational speed of the stars, this mass needed to be several times more than the mass of all the stars in the galaxy combined. Later, it was revealed that the same situation was true in all other galaxies we looked at. Their masses were all much larger than the masses of their visible, luminous material, their stars. It quickly became clear. Something ain't right here. Scientists began investigating and theorizing, trying to ascertain exactly what this mysterious dark matter was all about, which, I remind you, we cannot see, but at the same time we can feel through its massive gravitational effect. Over the next 10 years, many different hypothetical candidates for the role of dark matter were eliminated one by one. There was one option that it could be some mysterious gas or dust which fills all of interstellar space. But the fact is that these substances, being normal matter, always emit radiation. And, whatever one may say, if there were so much gas or dust in the galaxy, we would see it, as in this photo showing emissions from dust. Additionally, gas and dust are created within galaxies. And as observations and calculations revealed, this mysterious dark matter must stretch many thousands of light years beyond a galaxy's visual boundaries, forming a kind of halo around the galaxy. There was the possibility that this mysterious dark matter could just be very cold corpses of billions or trillions of dead stars, and that they are so small and weak that we simply cannot see them. White dwarfs, neutron stars, and maybe even some black holes. But this hypothesis was also refuted by observations. Indeed, if these objects existed in such large numbers, many times greater than the stars themselves, then we would have noticed them via a phenomenon called microlensing. This is when cosmic objects distort light from something behind them. But throughout the period of observation, there were too few such events, and this proposition was also excluded, leaving the question open once again. It seemed that the only option remaining was to assume this matter consisted of much more exotic particles than our usual protons and neutrons. The problem is, if we cannot actually see these particles, that means that they should not be able to interact with light in any way. They cannot absorb it or radiate it. From the set of particles already known to us, neutrinos seem to be the best possible candidate. Indeed, these ultralight particles are everywhere. Literally, at this very moment, billions of neutrinos, born in the bowels of the sun, are flying through you, and you don't even begin to suspect their existence. These insubstantial particles interact with almost nothing and do not emit or absorb light. They seemed the perfect candidate for dark matter. It was thought that, perhaps, all the hidden dark matter was just an enormous amount of neutrinos that we couldn't see. If only it were that simple. Although the exact neutrino mass is unknown to us, we know for sure that it is no more than 1/10,000,000th of the electron mass, and this is about 100 times less than the mass needed to explain the colossal, gargantuan amount of dark matter. So what's next? This mysterious material is not an ordinary particle such as protons and neutrons. It's not neutrinos. What is it then? Black holes? No other suitable particles were found within the standard model of particles known to us. The only possibility, then, is to seek answers beyond it. There are two main types of exotic candidates. We don't know whether such particles exist in nature, but either of these candidate types, if they exist, could fully explain the bizarre mysteriousness of dark matter. The first category is the so-called WIMPs, weakly interacting massive particles. This is a certain class of particles that arise in supersymmetry theory. In this theory, they are 10 times heavier than protons and neutrons and interact only through the weak force. Scientists use huge reservoirs with liquid xenon to try to detect them. If WIMP particles exist as a huge cloud throughout our galaxy, then at least a few of them should interact with the xenon nuclei in the laboratory and emit light that could be detected over the many long months of observation. However, there have been no positive results, which greatly narrows the possible parameters, for example, the masses for these hypothetical particles. The other category of particles is axions, also hypothetical, which are predicted by the theory of nuclear interactions. These particles, unlike the previous ones, are extremely light, mere billionths of the mass of an electron. But again, theoretically, there could be an awful lot of them. One of the properties of these axions is that in a very strong magnetic field, they can be transformed into photons, that is, light particles, and back again. It's this theoretical effect that allows scientists to hunt for these particles. If we take a small chamber with an enormous magnetic field inside and shine photons there, then if we wait a very, very long time, some of the photons should turn into axions, which we would notice. But again, this real-world, multi-million-dollar experiment has yet to produce any direct results. But as is generally the case in science, the lack of a result is also a result. So, over the past 40 years, we have finally come to realize that we cannot explain the presence of this mysterious mass in the universe with either interstellar gas or dust, or dead stars and dwarf stars, or from any particles known to science. In spite of this, observations and experiments have helped us to remove from contention the existence of huge classes of different variants of WIMPs and axion-like particles. considerably narrowing the range of our search in just the last few years. If future experiments do not yield any positive results, then physics will once again, in its long history, be faced with a colossal problem. Because it turns out that for all the complexity and variety of known particle physics, we still don't know what constitutes 85% of the matter of our universe.